please.
Yeah. Thank you. Thank you, Carmelo. Good morning, everyone. So indeed, I was asked to summarize multi-messenger astrophysics. And so maybe a decade ago, multi-messenger astrophysics results would have meant to summarize observations of photons and cosmic rays. But so in this decade, we've had the wonderful privilege to see the two missing messengers, both high energy neutrinos and gravitational waves, astrophysical neutrinos. And so in this talk, I'll try to say a little bit about all of them. So of course, all the four messengers are connected. So most likely the sources of cosmic rays are luminous sources, and the cosmic rays produce neutrinos and photons in their propagation. And some of those sources are likely in binary systems, and if they happen to be in closed binary orbits, then they might also eventually emit detectable gravitational waves. So the idea that has been discussed quite a bit in terms of multi-messenger astronomy is that it is remarkable that the energy flux, the diffuse energy flux of the three different messengers, gamma rays, high energy neutrinos, and the extragalactic cosmic rays that are down there, have a very similar energy flux. And so this could be a sign that they're produced by the same source population. It could also just be a coincidence that they're being produced by different populations with the same emissivity. And so I will discuss what we know about this today. And so what I have planned for this talk is that I'm going to go pairwise between the different messengers, so starting with photons and gravitational waves. So here, the one event there is to talk about is this remarkable GW 170817 that was immediately within a microsecond followed by a GRB with the same name. And so this was an event that was a wonderful confirmation of the model that predicted that short GRBs originate in the merger of such binary neutron stars. This was an event which was observed. So it is thought that this was a jetted short GRB, but we observed it off axis. So if it hadn't been for the gravitational waves, it wouldn't have attracted all that much attention. The Fermi GBM sees such GRBs very all the time. And it was localized in this galaxy, which is very nearby. So this was one of the fortunate things. The gravitational wave detectors are more sensitive to GRBs nearby. And so that was the first event. So this was an event that was seen to have basically to emit synchrotron radiation and all wavelengths from radio to X-rays and some gamma rays. And so these are thought to be truly multi-messenger events in the sense that they're also predicted to produce high energy neutrinos. These are models which are shown here. This was an event that was nicely in the field of view of Auger and IceCube, but there were no neutrinos detected. But that could be because it was an off-axis event. It could also just be that these models are optimistic. This we don't know yet. And it has also been discussed that these binary neutron star mergers and the short GRB that follows are also very good sources of cosmic rays, and it has been shown that they can produce cosmic rays up to the ankle of the cosmic ray spectrum. So that's what we've seen so far, the gravitational waves and the photons, but this is one of the events that could be absolutely multi-messenger. Maybe next time we'll be lucky. Okay. So that now going on to photons and cosmic rays, here the most exciting topic for me is the arrival directions of the highest energy cosmic rays, which will be discussed in a dedicated talk tomorrow, but just to briefly summarize the status of that. So at the highest energies, there are intrinsic anisotropies seen in the arrival directions of the cosmic rays, they're not yet all that significant, but there is also an at this energy with this energy threshold, but there are correlations with cataloged objects in excess of what would be expected from isotropy, and the most significant one is that with of the highest energy cosmic rays with starburst galaxies, and at the moment this search has produced excess events with post-trial significance of 4.2 sigma. Another very interesting excess is seen around the region of Sene. This is actually a rather extended region, is what James was mentioning yesterday, the Council of Giants. And so you can see that this is an excess of events that has been growing in time since 2006. Pretty steadily, and it is at present at the 4 sigma level. So another interesting result there. So at slightly lower energies, we have the actual detected anisotropy. This is the dipole anisotropy that Auger has reported, and we also see that anisotropy grows with increasing energy, but the direction of the dipole is consistent with not really changing with energy, or it might be slightly, as you can see here. This we cannot tell yet. And we don't know what the origin of the dipole is yet, but there have been several models that have been shown to be consistent with that dipole. So it has been shown that that dipole is consistent with being produced by the large-scale structure, that is all the nearby galaxies as mapped by this infrared galaxy survey. It was also shown in a work that I was co-author on that it could also be that such dipole is produced from the population of nearby jetted AGN, so the nearby radio galaxies. And it has also been shown by other authors that it could be simply one dominant source or two. So it could be that it's just Centaurus A and M82 or some combination of the two that produce such a dipole. So at present, we can't distinguish between those models, but it's interesting that we can reproduce the dipole with several models. Okay, so now I'll switch to talking about neutrinos and cosmic rays, and kind of asking the question whether these two could have a common origin. And I mean, I'm always talking about the extragalactic cosmic rays above the angle. And here I will first say what we know about each of them individually a little bit before I come to talking about joint, possible joint origin. So first, regarding the cosmic rays, we do not know what the sources of the highest energy cosmic rays are, but what we know is something about their number density. So here I wanted to illustrate that if we have few sources of cosmic rays, these are the red points, and tens of cosmic rays, let's say, above a certain energy range, then we expect to see clustering around the sources and some deflections related to the magnetic field, which are hopefully low at the highest energies. But if the sources of the cosmic rays are more numerous than the cosmic rays than we detect, and every source has produces the expectation value is a fraction of a cosmic ray, then we don't expect such clustering, such strong small-scale clustering. So this was the search that was done by the Auger collaboration. They looked at the highest energy events above 70 eeV, where the deflections should be small, and based on this argument, placed a lower limit on the number density of the sources of the highest energy cosmic rays. So if we are conservative and assume this 30-degree deflection, then we can still place a lower limit of the order of 10 to the minus 5 per cubic megaparsec. So what does this mean? It means that the sources of the cosmic rays are not that rare. Otherwise, we would have expected to see more clustering. And so sources like GRBs or jetted tidal disruption events or blazars are excluded by this argument, so long as we don't have higher magnetic fields here. Okay, this is what we know about the cosmic rays. Now, what about the neutrinos? For neutrinos, we can't do quite the same exercise because they're not confined to the GZK volume. They come from the entire observable universe. Instead, we can, so first of all, we can express the flux that is observed in IceCube. So we can, so if we multiply the number density of our favorite source population and the characteristic neutrino luminosity, then we can get an energy density of neutrinos, and we can convert that to the flux on Earth. And so if we demand that our source population produces the entire neutrino flux that IceCube has detected, then we can place all sources on that red line. So here we have the rarest and most luminous sources, which are high luminosity blazars, all the way down to very common sources, or normal galaxies are up here, and they don't have to emit all that many neutrinos individually to sit on that line, which describes the IceCube flux. Okay, so now, given what we have seen in IceCube, and whether we have seen point sources, and whether we have seen small-scale clustering, which we call multiplets, we can say how far the nearest source of a given luminosity can be, given that whether we detected or not point sources. So in IceCube, there are no 5 sigma point sources yet. So we can say that a very luminous source has to be far enough away that it didn't produce such a detection. And this allowed us to place a luminosity-dependent upper limit to the number density of the sources of the neutrinos. And that's what it looks like. So that argument excludes very rare and very powerful sources like these blazars. We can do the same for transient events, and that also, so by that argument, sources like GRBs and jetted TDs are also excluded as the main sources of IceCube's neutrinos. So now if we put this together with what I was saying before about cosmic rays, we see that both populations seem to favor numerous, non-rare source origins. And so in that sense, a joint origin is allowed by this argument. And it would be somewhere in this space here. Okay, now we can take this question further and ask, if the cosmic rays and the neutrinos are produced in the same source population, should we see correlations of their arrival directions? And so naively, we might answer no, because the cosmic rays have at the highest energies where the deflections are small, the cosmic rays have a horizon of a couple of 100 megaparsecs, but the neutrinos have a sort of span the entire observable universe, so only a very small fraction of neutrinos would come from the GZK volume. However, this is an argument that depends on the redshift evolution of the source population. So typically, when we look at the distant universe, we see sources so we see at high redshifts, there are more sources. So we know that in the past, there was more activity. So most source classes had a higher number density in the past. And so the neutrinos would come preferentially from those high redshifts. And that includes, so this is just the number density at different redshifts relative to today. And so sources like GRBs, starburst galaxies would follow this trend. But there are a few source populations which have a negative redshift evolution, so they are fewer in the local in the distant universe, and they're mostly present in the locally at low redshifts. That includes low luminosity blazars and tidal disruption events. And if we're in this regime, then maybe many of the neutrinos come from the same volume as the same distances as the cosmic rays. And indeed, I just will briefly say here, this is what I wanted to show with this plot, that if we are in a situation where the redshift evolution of the sources is negative, like low luminosity blazars, then something between 15% and 50% of neutrinos come from the same volume as the highest energy cosmic rays. And this is a statement that depends exactly on what energy of cosmic rays we assume. So, and also what composition. Of course, so here I have just shown an illustration for protons. Okay, so it's not completely hopeless if we're in this regime. This is what I wanted to say. If the sources have a negative redshift evolution. And so this search has been done by the telescope array, Auger, Antares, and IceCube collaborations. But basically what they found is that there is at present no signal of correlation of the highest energy cosmic ray and neutrino arrival directions. So how can we explain this? There was a nice study done by authors including Arjen, who's here, where basically they did what I was describing before with numerical simulations. And what they found was that they expect to see a large number of correlations, so a statistically significant correlation signal between neutrinos and cosmic rays, if the number density of the cosmic ray sources and the neutrino sources is low. However, unfortunately, this argument that I made before about the non-observation of multiplets in IceCube basically rules out this favorable parameter space, meaning that we are unlikely to see such correlations because that parameter has been already closed by IceCube. So joint origin is still a possibility, but not in a regime which we can easily test with correlations. That's my point here. Okay, so I'm going now to switch to photons and neutrinos, and this is the last I want to talk about, but I have quite a bit to talk about on this topic. And here we can ask the question again, if the neutrinos and the gamma rays come from the same population. So here we happen to know that blazars are the dominant source of gamma rays in the universe. So really the question is whether the neutrinos come from blazars as well. And so why blazars? Of course, they are the dominant source population of extragalactic gamma rays. So almost every source on this map which is not in the galactic plane, which is circled here, is a blazar. So these are the jetted AGN where we're looking directly into the jet. And we see the beamed emission. And so it's logical that they attract a lot of attention as cosmic ray sources, possible cosmic ray sources. So what we think is happening is that electrons are high energy electrons are somewhere in the jet of the blazar. And in addition, if there are relativistic protons in the jet, then they're interacting with the photons either in the jet or close to the AGN, and they produce gamma rays and neutrinos. Now, the energy of the neutrinos that comes out of this jet is regulated by the kind of photon target field that we have in the source. So close to the AGN, we have high energy ultraviolet photons which come from the accretion disk, and further out, we have infrared photons which come from the dust that shrouds the most powerful AGN. Not all AGN have this. So if the neutrinos are produced in these interactions with the infrared photons, then they have high energy. They peak at 10 to the 18 electron volts, Otherwise, if they come from UV interactions close to the black hole, they have a PeV energy. Okay, so here I have plotted the ice cube data and upper limits at the highest energies from Auger and ice cube, and I'm overlaying several of what I would call classical blazar neutrino models. And what I want to draw your attention to is that actually they don't describe the ice cube data very well. All these classical models thought that the neutrinos from AGN have to come from these very high energies that I was showing before. Now, in addition, we can do a search where we look at whether there is excess neutrino signal. So this is the point source selection from IceCube from the known directions of blazars. And so this has been done by the IceCube collaboration, and there is no signal found. And this has allowed to place a rather good upper limit of order 20% to the contribution of blazars to the diffuse IceCube flux. And very recently, about 2 weeks ago, there was a new paper where they looked only at the brightest MEV emitting blazars and found a limit of order 1%. Okay, so this kind of breaks our beautiful picture that maybe all the sources have, all the messengers have the same origin, since blazars don't seem to be the origin of all the neutrinos. But this isn't really the end of what I want to say about blazars, because in addition, there have been searches which have found varying levels of excess of correlations between blazars and neutrinos. And specifically, this event you will have all heard about, there, in addition to these searches which look at the bulk of neutrinos, which are most of them atmospheric and some astrophysical signal, we can look at individual very high energy neutrinos, and this is shown here. This is a famous event in which a neutrino, a 300 TeV muon neutrino was seen in coincidence with a 6-month flare from this blazar. And so the chance probability to see such an event is low, which gives this a 3 sigma significance. And many people analyzed this event and all concluded that this source can have produced a fraction of a neutrino, about a 20th of a neutrino. So I want to briefly say, what is this upper limit here of a 20th of a neutrino? So basically, this comes from the requirement that while we produce neutrinos, we don't overshoot the X-rays or gamma rays of this source. So they give us an upper limit to the neutrino production in this source. But it's important to keep in mind that actually to get this kind of flux requires a proton luminosity which is not typical in the blazar population, because the diffuse limits place a stronger upper limit by about a factor of 100 to the proton content of blazars. Okay, apart from that, this just means if we have 20 flares of such with such intensity, then we expect to see one on average somewhere from one of the blazars in the universe. All right, and since then there have been a few more alerts. I think I'll just not talk much about this, but there have been 4 more, 3 of which have actually been modeled by there has been theoretical modeling, but they weren't as significant as the original detection. Here I showed 2 of those 3, so I wanted just to bring your attention to the fact that they're actually rather different blazars, so they're not from the same class. One of them is what we call a flat spectrum radio quasar, which actually wasn't flaring at the time of the emission, and one is an extreme blazar, which is not that luminous, but has its energy emission. It's a very high energy, so in that sense, it's an extreme source. And basically, for all these sources, we found through modeling that they all can have produced about 1/10 of a neutrino. So that is consistent statistically with detecting one neutrino. But generally, they require a very high proton content. Maybe I can just quickly say that if the neutrino production happens in interactions with this infrared field that I was describing before, then we can really relax this need for high proton content. So I find this an appealing feature of the models, and this corresponds to this source here. However, then the peak of the neutrino emission is at 10 to 17 electron volts, so in an energy range where IceCube isn't that sensitive. So then we need to be looking at future detectors that are optimized in this energy range to find the blazar neutrinos. Okay, so I'll switch to gamma ray bursts. They're also spectacular gamma ray emitters. Here only 200 that have been detected with the Fermilab are shown, but there are another 2,000 in the last decade detected with the Fermi GBM. And in GRBs, much as in blazars, we have all these different photon fields, and depending on which photon field exactly in which radius in the GRB the neutrinos are produced in, we expect a neutrino spectrum at a slightly different energy. So in that sense, it's pretty analogous to blazars. And so what has been done here is a similar stacking likelihood stacking analysis with IceCube, as I was showing for the blazars before, where in collaboration with the Fermi GBM team, they analyzed the directions of 2,000 GRBs and basically found no signal, which has allowed to place a rather strong upper limit of 1% to the contribution of GRBs to the IceCube neutrino flux. Now, if we look not only at the prompt phase of the GRB, but allow a large time window of 14 days before and after the burst, then the limit is somewhat relaxed, and it's of the order of 20%. Okay, what about pulsars and galactic cosmic rays? So here pulsars are also very good gamma ray sources, and Fermi has detected more than 200 galactic pulsars. Most of them are in the galactic plane. And there's also this cosmic ray flux, which probably powers a lot of this gamma ray emission. So here I would say, if we look at the sky map that IceCube has produced, then we don't see as strong an excess of neutrinos as we do in the gamma ray map. This is basically what an analysis done by IceCube and Antares looks like. And what they've found is that there is an upper limit of the order of 14% to the contribution of galactic cosmic rays to the total high energy neutrino flux. And if we take individual source classes like TV emitting blazars, X-ray binaries or microquasars, then there is an even stronger upper limit to their contribution. Okay, then I want to talk about non-jetted AGN. So these are 100 times more numerous than the jetted ones. But actually, if we look at the gamma ray sky, there are very few. Fermi has detected about 10. But if we look at X-rays, hard or soft X-rays, they're the dominant extragalactic emitting population. They are these red points shown here. And so IceCube IceCube collaboration members have done a similar stacking, likelihood stacking analysis in which they look at the arrival directions of the neutrinos and see if there is an excess in the direction of non-jetted AGN. And interestingly, they find a mild excess. It's currently at the 2.6 sigma level. And so if this excess is interpreted as a true signal, then these non-jetted AGN could account for up to 100% of the total neutrino flux. This is shown here with this blue. This is the contribution of these AGN to the total flux, and this is here the IceCube neutrino flux. So this is interesting, but it will take a very long time to grow if it's real. In addition, there is NGC 1068. This is a prototypical nearby non-jetted AGN, and it also has high star formation activity. And looking at the IceCube data, it has been found that there is an excess of events in the direction of this source. There are about 50 neutrinos in excess of what we would expect from background. And the post-trial significance of this is 2.9 sigma at present, and it is a very soft spectrum. It has an ether minus 3.2. And so what is this? So here, if the neutrinos are being produced in a non-jetted AGN, there are several models which sort of predict that there is a shock surrounding the accretion disk or related to an AGN wind. And basically there we can imagine shocks which will allow for diffusive shock acceleration or magnetic reconnection. So there are several models how this could be done. And many groups have tried to see whether they can come up with a model that explains this observation. So here what I want to summarize that basically it is possible. So there are several models in which the NGC 1068 produces these 50 neutrinos that IceCube has seen. And generally, all these models have to be, the neutrinos have to be produced very close to the core of the AGN. Otherwise, there's too much gamma ray emission, which violates the gamma ray observations. However, again, as I said before about the blazars, the cosmic ray content of this source has to be about 100 times or maybe 50 times larger than the population of non-jetted AGN in order to explain this observation. And this is the only caveat. Okay, so now I want to talk about tidal disruption events. And actually, tidal disruption events are not gamma ray detected. I just drew some points on this map. There are no detections in gamma rays of tidal disruption events. And here, there is a subset of tidal disruption events which form a jet. So there is an accretion disk that forms, and in addition, in some instances, there is a jet. And it is these jetted tidal disruption events that originally people were very excited about and thought, okay, these might be good cosmic ray and neutrino sources. At present, only 3 jetted tidal disruption events have been detected, and those there has been a stacking analysis within IceCube which has shown that these are consistent with producing at most 3% of the diffuse flux seen in IceCube. There are also non-jetted events. They are way more numerous. And recently, there have been 3 tidal disruption events associated with 3 high-energy neutrinos from alerts. And the combined significance of these 3 events is 3.7 sigma. So, and what's interesting is that all of these have been detected, the neutrinos have been detected 150 days or more after the onset of the tidal disruption. So here, these are all 3 the events do not have a jet. So any model that explains these events has to be more like what I was saying before about NGC 1068, where the acceleration happens somewhere around the core of the AGN, or maybe here, okay, there is a minuscule jet here, but it's supposed to be understood that there is no large-scale jet. And this is very well constrained by radio observations. So from modeling these 3 events, what has been found out, actually I was only involved in modeling the first one, but I think the statement stands for all 3. We can come up with models that again give about the fraction of a neutrino, so statistically consistent with observing 1 neutrino. But again, just like for the blazars and the NGC 1068, the proton content required is extreme and atypical of the population. So it seems that maybe we're seeing some really extreme hadronic events, but we don't have any obvious electromagnetic way to say which these events should be yet. So this is the current state of these alert searches. So here I almost finished, and I have sort of grouped together all the results from stacking so upper limits that have been derived to the population of of any of these populations to the total ice cube neutrino flux. So some of these results I mentioned before. So for example, blazars are well constrained, so are galactic sources, so are GRBs and tidal disruption events. They all seem to produce no more than about 30% of the ice cube diffuse flux. And so are clusters of galaxies that I didn't have time to talk about. Now, there is no search that I'm aware of the contribution of starburst galaxies to the ice cube neutrino flux. That's why I put it here as 100%. And there is this weak signal from non-jetted AGN, which is consistent with producing almost all of the ice cube flux. And then here you see that supernovae are also not constrained. They are in principle able to, these are core collapse supernovae, not from our own galaxy, but extragalactic, and they're in principle also consistent with being the sources of the neutrinos. Now, I want to say, first of all, that these are model-dependent limits, so you shouldn't take them, you should take them with a grain of salt, because if we change the weighting of the different sources, these percentages just change. And also, I want to remark that the sources which are unconstrained are basically unconstrained because they're very numerous. So it's not easy to constrain them, whereas rare sources have already been constrained. And this goes back to that other result I showed, where it seems that the sources of the high energy neutrinos are very numerous. And those are independent arguments, so the clustering constraints and these stacking analyses. Okay, so where do we go from here? We have a fantastic network or multi-messenger network and different experiments. And in addition to the different experiments covering all the different messengers, we have infrastructure to communicate alerts to allow for rapid follow-up. And we have theory groups working hard to interpret every alert that is detected. And of course, from here, things will only get better because there are planned upgrades to every one of these 4 messengers. So planned neutrino new detectors and larger detectors, same for ultra high energy cosmic rays, same for gravitational waves, and also very sensitive telescopes at all wavelengths. So in that sense, I think we're in a good place to wait for the next multi-messenger events. So here I want to summarize. So I argued that what we observed so far seems to suggest that the sources of the high energy neutrinos and of ultra high energy cosmic rays are not the rarest source classes, so they're relatively numerous. And in a sense, this is unlucky for us because it's more challenging to find them. However, there are new and more sensitive instruments being deployed for all the 4 messengers, and theorists are working hard also to sort of, along with experimentalists, to interpret the observations. And in that sense, I feel we're in a good place waiting for the next multi-messenger events. And with that, I'll stop and thank you.